knows a lot about the science stuff. Professor Dave explains.
We are in the process of looking at a number of reactions which deal with the construction of alkenes, or olefins, by joining two carbon-based fragments, which come together to form a double bond between them. The first reaction we described of this type was the McMurray reaction. Another important approach to synthesizing alkenes is the Peterson Olefination, first described by American chemist Donald Peterson in 1968. In its early applications, the reaction consisted of two stages. First, an alpha-halo silane is metallated. This can be done using magnesium to form the Grignard reagent, or it can be treated with a lithiating agent to give a lithium carbanion. These reagents are very nucleophilic and will react with aldehydes or even ketones at low temperatures to yield a beta-hydroxysilane, like this one here. These intermediates are usually isolated and treated with acid or base, which causes rapid elimination of a silanol and formation of the olefin, in this case a monosubstituted alkene. One of the main advantages of this reaction over other olefination methods we will describe is that the co-product, trimethylsilanol, dimerizes spontaneously to yield hexamethyl disiloxane, which is volatile and can be removed by evaporation, thus leaving no other substance in solution but the product. The reaction works with many substituted silanes, such as triphenyl or tert-butyl dimethyl, and the starting silane can be substituted with alkyl or aryl groups. In this case, one obtains a 1,2-disubstituted alkene, although the issue of isomerism presents itself as usual. In this case, because the first step, the addition of the alpha-silyl carbanion to the carbonyl, is irreversible, and the elimination step is stereospecific, as we will see, the stereochemistry of the nucleophilic addition is stereochemistry determining. If the R1 substituent is moderately bulky and the silyl group is TMS, given the longer carbon-silicon bond versus a carbon-carbon bond, most alkyl groups are considered bulkier than TMS, and the addition reaction can be quite stereoselective. To illustrate this point, let us consider the transition states of the addition and represent them as the Newman projections of their products. Let us assume that the transition states resemble the products to some extent. In the products, torsional interactions between groups R1 and R2 are strong in the erythro product, but weak in the 3O product. This leads preferentially to the formation of the 3O product, although these interactions are incomplete in the transition state and the selectivity is moderate. If we desire the erythro product, usually a bulkier silyl group, like triphenyl, increases the torsional strain and makes the erythro product more favorable. Once the addition is complete, the elimination must be carried out. Let us assume that we have obtained the 3O product in good selectivity. Now we have two choices for the elimination, acid or base, and these choices lead to opposite stereochemical outcomes. With acid, protonation of the alcohol takes place, turning this functionality into a leaving group. The most favorable conformation leading to desilylation and formation of the alkene is one in which the silyl group is antiperiplanar to the leaving group. This occurs because the orbitals used for the elimination are already perfectly aligned to form the incipient double bond, just as we learned in a tutorial regarding E2 on cyclic systems towards the beginning of this series. Sometimes mineral acids like hydrochloric or sulfuric are used for this elimination, but often Lewis acids, such as BF3 etherate, are preferred. If instead we use a base to trigger the elimination, the base, usually a strong one like potassium hydride, deprotonates the alcohol function, which can then bind the silyl group, forming a cyclic silanolate. These silanolates have a tendency to fragment and yield an olefin. The silicon-containing product is, after aqueous workup, the same as obtained with acid, hexamethyl disiloxane. Due to the syn-coplanar nature of the elimination transition state, in this case the olefin that forms is exclusively E. One thing to be aware of is as follows. It is evident that the primary product of these reactions, an alkoxide, will tend to fragment in situ. And if the Z-olefin is desired, this primary product must be quenched with acid below room temperature, and thus before it has a chance to fragment at higher temperature, yielding the E-olefin instead. The silyl-containing nucleophile can also be functionalized, like with a nitrile, ester, or an imine group. In these cases, the primary product eliminates even more readily, and it is very difficult to prevent the fragmentation, which yields an unsaturated nitrile, ester, or aldehyde after acid hydrolysis, as shown here. The Peterson Olefination has frequently been used in the synthesis of natural products, or unnatural substances of medicinal interest. For example, Professor David Van Vranken at UC Irvine has synthesized the terpene 3-hydroxybakuchiol, using in the key step the Peterson Olefination. In this case, the reaction proceeds as expected, yielding in high selectivity the 3O product. This alkoxide fragments quite readily below room temperature with almost complete E-selectivity. The benzyl protecting groups are then readily removed to yield the natural substance. As we have demonstrated, the Peterson Olefination is a useful tool in synthesis and allows both stereo control in the olefin product and easy removal of the coproduct, which in many cases is the volatile hexamethyl disiloxane, thus facilitating product purification. For these reasons, this is a reaction that every practicing organic chemist must be familiar with.
Thanks for watching. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.